Daryl, and this is Programming in Any Language. We're working with C# right now, but the principles are the same. Master these principles and you can easily jump to any other language. Today we're going to look at the concept of strings. When we work with strings, it's important to understand what they are and how the computer sees them. In order to do that, we have to understand how the computer communicates with us. The computer can't talk. In fact, it can't hear. But what it can do is acknowledge a pulse. In other words, it knows what on is and what off is. That's it. That's a binary system or base 2. The computer is a wee bit smarter than a rock. Now let's look at us. Since we can't talk to the computer in English or any other language for that matter, we need another form of communications. We could use base 2, but that's pretty confusing to us since we are used to using base 10. Including our thumbs, we have 10 digits on both our hands. We can count to 10, just with our fingers. If we want to go to 11, we need to bring in a friend. And with a friend's help, we can go all the way to 20. A few more friends, we can go higher. Can we do the same for the computer? Well, yes, we can. The binary system the computer uses is that of a switch. A switch is either on or it's off. If it's on, we can treat that as a 1. If it's off, we can treat that as a 0. So using a switch, we can count from 0 to 1. Take a look. Okay, let's take a look at a series of switches we've got here. I'm going to throw one on right now. The computer is nothing more than a series of switches. Each switch we call a bit. When on, the bit is considered a 1. When it's off, it's considered a 0. Take it right here. We got one that's off. Now it's on. Off, on. Simply like that. And this switch can represent the numbers 0 through 1. If I turn it off and I add a second switch to the mix, I now have a second bit. And if I turn this one on, it's actually a 2. It's in the second position. So it's a 2. So if I set both switches off, I've got 0. If I throw this one on, I have a 1. This one's off and this one's on, I have a 2. And if they're both on, I have a 3. A little confusing at first, right? So let's take a look at a third switch to clear it up a little bit. We'll add this third switch right here. And now if I throw it on, we actually have a 7. How are we getting that? Let's take a look at power. If I add powers to these things, you can see that you've got a number on top of here. These are the values of the switch are always going to be either 0 or 1. The multiplier on top is how much they're actually worth. So if you have 1 here, it's going to be 1 times 1 or 1 times 0, which is 0. If up here, it's going to be 2 times 1, which is 2, or 2 times 0, which is 0. This one is going to be 4 times 1, or 4 times 0, which is 0. So these values are going to represent something. So we can actually put a decimal equivalent on this thing and take a look at what it adds up to. And we throw this switch on, we see a 1. We take it off, turn this one on, we've got a 2. Throw them both on, we've got a 3. Okay, let's turn these off and turn this guy on. We got a 4. 4 times 1 is 4, plus 0, 0 is 4. Add this, it gives us a 5. 4 times 1 is 4, and 1 times 1 is 1. Add them together, you got a 5. Throw this one on, you've got a 2 times 1. So 4, 2, 1 is 7. We can increase that, go ahead and add, let's get the power up here again. We have 8 going across there. Throw that on, and you've got 15. We can keep on going down the line here, and we've got an incredible number of possibilities that if we actually look at this. In fact, if we look at it, we can throw all these switches on, and we end up with 255 possible numbers here. That's actually 256 because you had 0 in there. Everyone's off. You've got them all sitting at 0. So we look at it from the standpoint of all of these on. 0 through 255 is 256 possible positions that we can actually have in the byte. And that's what this is called, a byte. 8 bits is a byte. By the way, if we add another byte to the right of this particular byte, it keeps going up. 128 times 2 is what? 256. 256 times 2 is the next switch. That's what? It's 1024, I believe. And keep on going up into a large number. So you're going to actually get a very, very large number if you actually were able to use 2 bytes. And we'll see that down the road. We'll talk about that. But right now we're interested in the ASCII code and how we're going to be able to represent or communicate with the computer. And 256 positions gives us a lot of power to be able to match to the character set that we might want the computer to understand. That relationship is called ASCII. ASCII stands for American Standard Code for Information Interchange. Computers can only understand numbers, so an ASCII code is a numerical representation of a character such as an A, or an ampersand, or an action of some sort.
The table you are looking at is the ASCII character table, and this includes descriptions of the first 32 non-printing characters. It's worth noting that the space decimal 32, sitting right around here, is actually a character. If you place a space between my first name in code and my last name in code, you are including an ASCII 32 character to do so. So it's literally another character in the alphabet. If you look a little further, you can see the numbers 0 through 9 represented as a decimal 48 through 57. Other useful characters follow, and then we have the capital letters A through Z. The lowercase alphabetic characters can be found in decimals 97 through 122. This represents 127 of the characters we have in 1 byte, which can be up to 255, 0 through 255. So this only takes a small portion, or half, of a byte's values.
ASCII was developed back in the day of teletype machines. And now the non-printing characters are rarely used for their original purpose. Looking back at our byte program, you can see how as the switches or bits that are thrown, the decimal number is calculated and the ASCII representation is displayed.
So to look at those ASCII characters, we can kind of play with this program a little bit and see what they represent. This program actually goes through all 0 through 255 characters of the ASCII codes. A few of them doesn't print because they're non-printable characters. If we take a look at this and start throwing some of these things on, we can start to find where the alphabetic characters might be. We'll go to a 64 perhaps and maybe throw a 32 on. We got a quote here. Let's try this one. I'm going to do a D, so let's turn that off. Turn here. I got A. Okay, there's an A. So 64, 32, and 1 is an A. Turn this guy off. Turn this one on. We got a B, C. Turn these off. You got a D, E, F. You're going to have a G in a minute here. There's a G, H, I, whoops, H, I, J, K, L, M, N, whoops, N, O. And then P will be this guy. Turn these all off. Q, R, S, T, U, V, W, X, Y, and Z, and so on the line. We can search for the capital letters too. I think we just go a little further out, perhaps. Well, what did I think of it? Let's really go out to one. Kind of knock these all down and see where we are. Yeah, no, it's not that high. That's right, because 127 is going to be your, if we go to like this, here's our, well, that's actually, we're in the small cars. When you get to the big ones are like 91, I think we've got. So 64 and 16, throw these guys on, and we've got, well, there we go. So G, A, down a little further. Okay, let's go a little bit, that's 90 something. The ASCII table 64. Let's see, an A is a 65. So if we go here, there's our A, there's our B, and here's our C and our D. So a little tough to find this way. You can see how confusing this would be. If we had to know this, it would be terrible. But we do want to know the fact that this stuff exists, because we will do some character manipulations down the road. So it's important to get a good understanding that this stuff exists, but you don't have to memorize this at all. Just the idea that 8 bits, or 1 byte, we use to represent the characters of the ASCII code.
So how does all this fit with strings? Well, every time you press a key on the keyboard, you are causing 8 bits to get arranged to match the character you have pressed. If you press my name, Daryl, on the keyboard, you are using 7 bytes, or 56 bits in memory, to be arranged to represent my name as a series of 1s and 0s. Take a look.
What we have across the top of the screen here is basically empty memory. There's nothing there. And this is going to simulate the keyboard that you're looking at, the series of switches here, the byte that you're seeing in place here. As we press the byte and press a D for the first name of my name, first initial of my name, we'll get up with a capital D. which is experienced here. And this goes up into memory. You can see it being thrown up in here. As we press another key, the A, for example, all the switches are thrown, and it too gets thrown up in memory over here. We'll end up with an R, a second R, finally the E, and we'll finish it off with an L and an L. And we end up with 56 bits or 7 bytes expressing my name in memory. And they come in sequentially like this. Now typically the computer is going to put something in the back of this thing to end it, so you actually have a termination byte, so to speak, that ends the memory. So any computer, any program you're working with knows that the string starts here, goes as far, and ends someplace over here. What that ending string is something the operating system is going to do for you, so you don't have to worry about it.
So when you create a variable, a couple things are happening in memory. For starters, the operating system is taking the name of the variable and storing that name, like name or str name or str phone or something like that, and actually putting that name in memory. It's sort of like storing that name in an index where it can identify the data type it represents as well as the location where the actual value is going to be stored. Like a book. You got a book on the history of the Civil War. The word Appomattox is probably in the index. Next to it is a page number that will tell you more about what Appomattox was. Similarly, if you have a string variable called str my name, the computer will store that name in an index. It will identify it as a string, and it will have the location address of where that actual name might be stored. The operating system will then be able to go to that location, pull the data, which might be my name, Daryl, and it will make it available to the program. The beauty of this is we don't have to know how this is done or where the data is actually stored. The operating system does that for us. All we need to do is declare the variable and assign a value to it.
So how do we declare a variable? Well, we go into the coding area for one thing. I'm going to jump into the code itself by double-clicking on an empty form here. There's nothing in it. And you see all the things that are sitting out here. We have a form load event right here that it just created because I clicked on the form. We have a form 1 initialize components. This will actually initialize the form for us when we run it. We also have the class up here. And inside the class, what I'm going to do is I'm going to declare some global variables right now. And I'm going to call them string variables. I'm going to create, let's say, a name. Let's try this. We'll say string, and we'll say str first name. And that's it. And I might put a comment on this thing. Holds first name from user. And string, str last name, and I might call this one holds last name from user. I might want to put a middle initial. I'll set this up, str mi for middle initial, holds middle initial, and maybe I want to put in a phone number. str phone holds phone number. What I've done here is I've actually declared 4 variables that are in memory here that will be hold data in memory. Where it goes in memory, I don't know, and I don't care. The fact is, they're going to be string variables. I'm declaring them as strings right here. I'm also including str in front of them, a little prefix, so that later on, if this code gets too big, I can easily tell by looking at this name that, oh, this is a string variable that I'm holding here. It does help. You don't have to use Hungarian notation, which I'm using. You can use something else, but then this is fine. This will work. It's an identifier for me. And these are all in the class area. They're in the global area, or they're also called field variables. Any routine underneath it can see it. This is not the best place to put variables many times, but it certainly is a good place to go when you're starting and you want all of your elements, all of your methods down here to actually see them. But we'll look at this more in detail later. But this declares the string variables. I don't have to know anything about memory. I don't have to know about where it goes, anything of that nature. I just have to know that they've been declared.
Up to now, all this has been about ASCII. In reality, today's computers use something called Unicode. Unicode looks like this. It's essentially it's ASCII with another byte in front of it. For our purposes, that leftmost byte would consist of all zeros, leaving us with the initial byte, which is ASCII. The leftmost byte was added back in 1991. Unicode is a standard first released in 1991, which covers most of the characters from all the world's written systems. It covers current and historical scripts, alphabets, symbols, emojis, and non-printable codes for controlling and formatting. At the time of this video, it contains almost 150,000 characters and is continually being updated by the Unicode Consortium. Doesn't affect us unless we choose to display characters from other languages. In that case, they're available to you. But for learning C#, or any other language for that matter, you can ignore Unicode for now.